Okay, so Adrian and I are going to talk to you about STEER. This is a two-part presentation. I'll give some general background on what STEER is, and then Adrian is going to present 3 case studies that I think will illustrate what it is. So what is STEER? Well, I'm not going to answer that now. I think it'll be really clear by the end. But simply put, what we do is we use engineering and economic analysis to guide what to build with speed and scale for the energy transition. And speed being that we all know that we have very little time. We have, every day we continue doing what we're doing. We're putting greenhouse gases into the atmosphere, leading to global warming. And second, the energy system is huge. Today, the majority of it is dominated by CO2 emitting sources. And so whatever we do, it has to be at massive global scale. Okay, so those are our motivations for this work. But I want to give a little bit of history that will give you a sense of how it came about. Also a sense of history, especially for all of those of you who are new here. This is really a magic place where people, you can come together, invent new ways of doing things, broaden out for first to the Stanford community and then much more broadly. And so this is going to be a fantastic, I think, example of the evolution of some of the work that we've done here in this regard. And having said that, we have John Wyant here. So Stanford has a huge, long history of energy systems analysis. And the Energy Modeling Forum began in what year, John?
1976-7.
Okay, 1967, 76. Jim Sweeney, John Wyant started something that continues to this day, which took a sort of a macroeconomic, economic approach to understanding energy transitions. So that was quite different than some work that I was motivated by. You heard about the Global Climate and Energy Project that Lynn Orr was so instrumental, along with other faculties, in setting up here. And basically our job as the leadership of that program was to make good choices about where should we be investing the resources that we had been able to pull together. And that's a really hard thing. Like if you know what something costs today or what it could cost in the future, you could say, okay, I want the cheapest thing, right? The cheaper it is, the faster it would be to speed and scale. But when you're inventing entirely new things, you have no way of knowing what it's going to cost, okay? So you need other ways of making good energy choices. So the Global Climate and Energy Project began to do some work, and we had a fantastic group of folks now that, anyway, they've all gone on to illustrious careers. 3 faculty members, Charlie Barnhart, Mick Dale, and Simon Davidson. Matt Pello being a leader now in industrial sector on energy storage. And Marcus Felgenhauer, who actually runs a big biotech intelligence firm. So go figure. But anyway, it was this group of students and postdocs who came together to start this work. And the idea was we could use a variety of different approaches to energy systems analysis to help make good choices about what we should be investing in. And here's a list of different models. They're integrated assessment models, which really take sort of a top-down view of the entire energy system. There are sort of bottoms-up energy systems integration model, where you consider, for example, how storage might integrate with solar panels or wind turbines. There's life cycle analysis, or there can be much more detailed work like using Aspen and so forth. So the goal was to use whatever tools we needed, really what was fit for purpose. And an example of some of the work we did is, is it better to use hydrogen or batteries for grid storage? Okay, it wasn't really clear. We did an analysis that basically said probably batteries were going to be better because it's more round-trip efficiency is more efficient. Another study we did is we realized that making batteries actually takes a lot of energy And in some applications, that they might be a significant consumer. If you look at what it took to build that battery in the first instance, the amount of energy you would ever get out of that battery over its lifetime was not very much. So it was like, we need to make batteries that are much more energetically efficient to build. Another example was, is it better to curtail wind and solar, or should we store it from an energetic point of view? If you're storing it, is it really worth the energy it took to build that battery? And then another one, believe it or not, 2013, there were people going around saying that photovoltaic cells had never provided energy to the world, the net energy, that it was taking so much more energy to build those solar panels. And our analysis, had said, heck no, that's not true at all. And in fact, that they were very beneficial. So that's the kind of thing we did then. So around this time, there were many Stanford students across the business school, the Department of Economics, the engineering school, earth sciences, who were really becoming interested in these questions. So a group of them, led by Patricia Levy, who was one of John Wyant's students, brought this whole group together that met for more than a year, shared all of their work. And out of this came the recognition that there wasn't really a community where this kind of work could be presented and nurtured and published and so forth. So she was the lead author on a paper called Macro Energy Systems Towards a New Discipline, making the point that for the energy transition, we were going to need lots of this energy systems analysis, and we should really begin to think of it as a new discipline with its appropriate places within university systems. So fast forward today, there is a whole community, and so what is macro energy systems? It's an emergent field and research community focused on large-scale, systems-level, long-term aspects of energy systems and their implications for other systems, including the environment, the economy, and human well-being. And now there are hundreds of people around the world. It's a very vibrant community. Here's a picture of them last year at their annual conference. And for anybody who's interested, there are actually now fellowships to join this community. So I encourage you to go to that website if you're interested. And again, that was organically grown here at Stanford. So that's what we did then. There's an opportunity to do more of this. Okay, so STEER, what's the origin story? I don't know how Will's going to like this. This is my version. One day, I'd been in Washington, D.C. for 2 years, and I came back, and Will said, hey, can I come over to your office? And he was very serious and really impressed me. He said, I want to make sure that our research team is working on the most important problems to support the energy transition. PhD students, thank you, master students, and so forth. So that was what he was thinking, and he knew that I did this kind of work. And having spent all that time in Washington, it was really clear to me that, we needed to think beyond the technology and the systems and so forth. We needed to think about energy security. We need to think about affordability and equity. And unless we could bring all those pieces together, we weren't going to be able to make the kind of progress that we needed. So that was kind of what was in my mind. And Adrian, as a former battery entrepreneur, said, well, I want to know what I should be focusing on building next. And so the three of us came together, and out of that came this program, STEER, that you're going to hear about. So basically, we look at the intersection between engineering, economic, and innovation through systematic analysis, techno-economic analysis. We identify what are the largest technological uncertainties, and then we figure out, well, how could you solve those, okay? So what does this mean in practice? Well, we're starting to think about supply chains. Of course, we think about the technology. We think about deployment and hurdles to deployment. We think about economic feasibility. Affordability is really key today, as we often hear. And then what is the value of this new technology broadly in the energy system to help us with speed and scale transform our energy system? So that's what this is. And so we chose to focus on particular topics. Energy storage, that was a natural outgrowth of Will and Adrian's research areas. We went on to think about nuclear, the nuclear fuel supply chain, really a critical issue. And then now we've started some new work on carbon capture, asking the question is there a way to make it much cheaper than it is today? So one other really critical element is we're interested in speed, right? So if you look at a traditional sort of academic approach to research, is that we initiate our research, we do a lot of work. After 2 or 3 years, maybe we're ready to publish our first paper. We put it out there in the literature after peer review and so forth, and eventually we start getting feedback, right? Well, that's a really long time. We don't have that kind of time anymore. So we wanted to turn it upside down. We wanted to integrate with other people working in these spaces much more quickly than that. So every project we undertake, we go through, first we have a lot of discussions. Is this something that really makes sense for us? Do we have something unique we can bring to it? Second, we learn a lot about it, and you'll hear some great examples of that from Adrian. We then invite the industry to say, come spend a day with us, and let's talk about this. Can you tell us what you think the biggest bottlenecks are, and is our thinking, are we going in the right direction? After that, we then spend some time doing really in-depth technical analysis. Then we have a forum. And again, we bring back all these people and we say as openly and as honestly, this is what we think we know about this problem. These are our conclusions. But you all know a lot more because you're in the field. You live this every single day. And tell us why we're wrong. We bring a lot of humility to bringing groups together so that we can have very open and productive conversations. Eventually, we revise things based on what we hear, and then finally it comes out. But by the time it comes out, there really aren't any surprises by the community. They already understand. They've given us feedback. So we find this very valuable. Most valuable is our team. We have an incredible group. We have a number of faculty members. Steve Davis, I don't know if Steve is here. Adam Bose, John Wyant. And so forth. We also have a team of postdocs and research associates shown here who really make this project. And I know for one, I find it really exciting to come to work every day to be with this group of people working on the problems we're trying to solve. So thank Will, thank Adrian for making this all possible. And over to you.
Thank you. Well, I think you guys now have a little bit of idea of what STEER is, but what I want to do is really walk through 3 examples to really paint it clearly what we do and really highlight not only the analysis that we do, but also the convenings that Sally just mentioned are essential to our process, as well as the impact that we're beginning to see from our work. So how many people know what this is that they're looking at? Energy storage, of course. These are the big batteries that are being installed into the grid today. I know that there are a lot of new people to Stanford just now by the show of hands. How many people of the new folks coming in are interested in working on energy storage? Great, that's a pretty good showing. So as many of you know, battery energy storage systems, or BESS, are enabling a new paradigm on the grid, right? They're enabling a lot more penetration of renewables for wind and solar when the wind is not blowing and when the sun's not shining. And so this is a critical aspect of the grid today. And just want to highlight also on the bottom left, we have the key folks here working on this, this specific vertical within STEER. Yulia is a PhD researcher here at STEER, driving a lot of this work. Now, just taking a look in 2020, December 2020, this is the planned and operational BESS installations in the United States. And what's remarkable is that just 4 years later, you can see the expansion of the deployment. And actually, Sally and I were just having a discussion earlier. A very minimal of all of this deployment was pushed by policy. And this highlights the importance of economics. And if we look at the economics, we can see that, of course, most of these batteries being installed are lithium ion. And of course, it's enabled by this massive and continued reduction in the cost of lithium ion. And so you can see this learning curve that lithium ion has enjoyed over the past 30 years since they were first industrialized. But really in the last 10, 15, we've seen this deployment on the grid, and that's been pretty remarkable. But one thing I want to point your attention to here is that you might notice a blip here in 2022. So what happened here? And this really does highlight one of the challenges with lithium ion, or really any technology, in terms of their supply chains. And so, as many of you may know, lithium ion supply chains may be vulnerable, and there are really three things that compound together that have added to that, for example, the example blip that we saw. And that is the minerals price volatility in the key minerals that drive lithium ion technology. That includes nickel, manganese, cobalt, and graphite, as well as lithium, of course. In addition to that, there are very concentrated supply chains, with a lot of that concentrated in China. And of course, the massive demand, as you just saw with the massive deployment of battery energy storage on the grid alone, not including EVs, that exacerbates everything else. And so just a couple key things to know. The price of lithium jumped more than $50,000 per ton in 2022 as a confluence of the Russian invasion of Ukraine, as well as the post-COVID supply chain challenges. And China owns more than 93% of the battery-grade graphite supply chain, and also the majority of the gigafactories. And so there is a challenge here. And so naturally, this presents the question of, is there a cheaper, more resilient alternative? And that, of course, is a question that many people jumped onto, and that is the sodium ion opportunity. Just by show of hands, how many people have heard of sodium ion? Great, that's most of you. And so, of course, many of you know that this is a cousin to lithium ion. It's basically the same fundamental working principles. You're just swapping the salt from lithium to sodium. Of course, it's a lot more complicated than that. But the basic premise is that. And there are three key things that have gotten people's attention, driving a lot of this innovation and investment. And that is, one, of course, sodium is a lot more abundant than lithium. And so that might suggest that the prices could be lower. Now, the key question here is, does this actually translate to lower costs overall? That is something that we'll dive into later. The second thing is that it's drop-in compatible, right? We are building all these gigafactories to make lithium-ion batteries by the billions over every year. And so there's the opportunity to leverage existing know-how and knowledge and infrastructure and just slot into and leverage those learnings. And the third thing, this is a little bit more shaky of a statement, but there's also interest in potentially improved safety of these technologies. And it's important to really deep dive into whether this is true, in what circumstances is it true, and what does it mean. So really, this is the impetus for actually the first question that we tackled at STEER. It's a very simple question, and that is, how quickly can sodium ion learn? Learning here, of course, refers to the massive learning rates that I talked about earlier. And of course, sodium ion is an umbrella. There are a lot of different technology chemistries that lie within. And so what technology roadmaps within sodium ion should we bet on to be the most competitive? Again, this is a very simple question, but with a very non-trivial answer. And so this is really the work that we did in this analysis, where we tied the understanding of supply chains. We work with partners like BNEF, or in this case, Wood Mackenzie, Benchmark Mineral. We understood what the market adoption forecasts look like by working with people like BNEF and Avicen as just a couple examples. But really the meat of the work is in this technology road mapping aspect, where we are modeling different flavors of battery cells, understanding how materials could or should evolve as we invest in innovation, and really mapped out, in this case, over 6,000 scenarios of how these roadmaps could play out if supply chains did X, Y, or Z. And like Sally mentioned in the beginning, central to our process is to engage deeply with the practitioners. So in this case, we had our work validated and analyzed by the folks in industry. Some of these companies are no longer around already, but this just highlights the dynamicism of this industry as well as the kind of the bleeding edge of innovation. So this led to a Nature Energy paper that we published early this year. But really the key takeaway here is on the left, and that is that the competitiveness of these sodium-ion roadmaps can really be dependent on two axes. The first axis on the x-axis is about energy density. Something that is a key takeaway is that energy density is key to economic competitiveness. And that might be a little bit counterintuitive, and you might often think that something for example, the grid doesn't need energy density. That might be true from a physical aspect, but in terms of materials intensity, how many kilograms of material do I need to achieve a certain amount of storage? That is key to competitiveness. Now, the second axis that we see here is the y-axis, and that's the supply chain scenarios. And we highlight basically that the supply chain scenarios in the battery materials, as well as the energy density that we're able to achieve, really define the competitiveness of this technology. And so the key takeaways, you can go read the paper if you want, but I'll just quickly go through them. And that is that, actually contrary to popular belief, sodium-ion cells may only be price competitive later, maybe in the next decade. And it's actually quite hard for it to be price advantageous and on an absolute basis. And to really accelerate that might actually require something to break in the lithium-ion supply chain. That's number one. Number two is that we recognize that this is not simply a matter of scaling. As technologists, which many of us in the room are, I think it's often easy to hide behind or couch behind the promise that when we get the scale, the cost will come down. In this case, we quantify it and we show that simply banking on scale is not enough and that R&D is fundamentally needed. And on that note, what things should we work on? Well, we can actually identify those key areas that we should focus on. So increasing energy densities, like I talked about earlier, but really using earth-abundant minerals and materials. That is a winning strategy. And so coming back, again, I want to highlight not just the analysis, but also the convening. And so again, once we have done our work, we pulled together, at this point, almost all the CEOs and CTOs in the sodium-ion space. Again, ask them to tell us why we might be wrong and challenge our assumptions, and really have a healthy debate about this before we kind of send this out into the real world. And so this is a commercialization forum we had in April of last year, and it continues to be a key kind of trademark of what we do at STEER. So that's the analysis, that's the convening. I want to highlight some of the takeaways here, or the impact that results from our analysis. So we do this loop-de-loop, this flywheel of our analysis, but I want to say three key things that I think are very important. The first is, since we have identified a spectrum of technology roadmaps that fall out of our analysis, we can actually put our money where our mouths are and actually go investigate those high-risk, high-reward research areas that we identify to be, if we could do it, then something big would happen. And so that's actually what we did. We seeded high-risk, high-impact research here at Stanford. And now this is getting the attention of some major industry players that would like to co-invest and kind of learn as we go. The second thing is actually helping guide the deployment of government funds from the Department of Energy. And so shortly after we published our analysis, the Department of Energy launched a new consortium called the Low-Cost Earth-Abundant Sodium-Ion Storage Consortium, LENS. DOE loves their acronyms. But this is a $50 million effort over 5 years involving 6 national labs, SLAC, which is co-located with Stanford, of course, being one of those key 6 national labs leading the effort. And the 4 key thrusts identified that really shaped the effort are really kind of along the lines of what we have published as critical roadmaps within our analysis. So we have academic activity, we have governmental activity, we also have private sector activity. And what our analysis did was actually to help changed the course of actually startup activities and their focus. Again, shortly after our analysis, there have been companies that actually agreed with our position, even though they were working on sodium ion, and in some cases decided to shut down, return capital to their investors, because in some cases that is the more higher integrity thing to do. And so this is very important in terms of kind of the outcomes, and I hope this gives you a flavor of the analysis here, not just resulting in a paper, not just resulting in a convening, but actual real-world activities and actions are falling out of this type of work. Now, if you recall, just now I mentioned the importance of battery supply chains. How many people know what they're looking at here? Just maybe surmise a guess, yeah?
Maybe the particles of a cathode?
Cathode? No. Sorry, this is actually the opposite. This is the anode. And this,
Would you expect like flakes for graphite maybe?
graphite is the anode. Well,
Exactly the substance.
oh, okay, yes. This is the anode. And what you're looking at here are spherical natural graphite powder materials that are used in the negative or the anode side of a lithium-ion battery. This is kind of continuing on our work, understanding the importance of supply chains, and identified that a lot of our battery materials are heavily concentrated in China, and it's important for resilient supply chains to have a diversified source. So this is work I want to highlight here again, led by Karan, who's a staff engineer here at STEER, as well as Swati, Hari, and others. And the reason we focused on graphite is that it's a critical component to lithium-ion batteries. It dominates almost all lithium-ion batteries today in all the negative electrode side of materials. And so this is a very important material to focus on. And not only is it critical to all lithium-ion batteries, the supply chain is also critically at risk. And so we are expecting a massive increase in the demand of graphite, but simultaneously, the majority of graphite, 93% of which, is actually made in China. And there have been attempts by our government to stand up domestic manufacturing, but this is still, as we'll show, quite challenging. And recent activities in industry have begun to highlight, again, the importance of this material. So it is now being tossed in along with other materials like gallium as geopolitical conflict materials that we can use to really stress economies. And so recent activities have placed, for example, significant tariffs on graphite coming from China. So we asked the question, one of the second questions that we asked at STEER is, what does it then take to onshore and upscale the graphite production in the West? And here it's important to understand that graphite has many different forms, has many different feedstocks, and the two primary routes are synthetic and natural. And we can really deep dive into the entire process flow chain of how these materials are made. So just to give you an example, if we zoom in on, for example, this bottom layer, synthetic graphite production, the level of detail that we're going here is really bottoms up, right? We can look at not only the flow chain, but also the electricity, the equipment, the labor, and the construction that goes into these supply chains to really understand both regional as well as scenario analysis. And so the high-level takeaway is that we find really stark contrast between costs of making graphite in the US and China. And so China, you can see the costs in China are seen here in the small bubbles on the bottom left, whereas those costs on the US side are on the top right. And we have on the x-axis for both synthetic and natural graphite, we have the cost of capital, so capital equipment. And then on the y-axis, we have the operating costs, so the cost of electricity, cost of labor, and cost of, for example, feedstock material. And so we can see that China is beating the United States on both CapEx and OpEx. And this is an important thing to identify. Now, the two gray lines that are bolded, that are diagonal, indicate the average selling price that are common today. And as you can see, the one on the further top right highlight the costs in China in 2022. And that was a decision, that is a point where many of these domestic companies decided to jump in with domestic manufacturing. And you can see that if prices stayed at that level, there are many production scenarios in the United States where we could still sell competitively into the market. But what's happened in the last 3 years has shown that the costs have fallen dramatically because of the continued innovations in China. And now very few, if not ever, if any, domestic manufacturing solutions can be competitive. And so this highlights what we might need to do in terms of policy, but also what we can do on innovation. And that's what I want to talk about next, is that apart from just highlighting the differences in cost, we can also identify the roadmaps towards cost competitiveness. And so we identify basically that supportive financing as well as process innovations are these two key levers that we can pull to get to a point of competitiveness here in the gray bar. And so again, I want to highlight the convenings that we were able to pull together here. This is just one example of a forum that we pulled together in Washington, D.C. in May of this year, convening across, again, the value chain from people playing in the minerals side all the way to the OEMs, the car OEMs. And I want to, again, highlight the impact of our work. This work has translated into helping assist the U.S. strategy on fortifying supply chains. But the other example that I'm really excited to share is our work to develop new spec sheets to accelerate the qualification materials. Now, as a former battery entrepreneur, I know that when I have two materials to look at, a graphite A and a graphite B, and I have their specification sheets, A and B, even if they looked identical, I would still have to spend about 3 to 5 years qualifying the second material, even if the specification sheets were the same, looked identical. And that just tells you that specification sheets today are wholly insufficient to capture the quality of materials and their performance, and oftentimes is the bottleneck for domestic players to actually make it into the market. Because to get to scale, you need to find the offtake markets to accept these materials. Oftentimes that is the electrification of vehicles market. And few startups in the country or anywhere in the world can withstand that much or can sustain for that long without revenue. And so we recognize that developing new spec sheets that can really accelerate, standardized spec sheets to accelerate adoption is a critical aspect that really should be done at an institution like Stanford and also SLAC, the co-located national lab that we are involved with. Because no one single industrial entity will go pursue this by themselves. So that's the second case study. The third case study is similar on the supply chain layer, but in a completely different vertical. Now, how many people know what we're looking at here? Yeah.
It's nuclear fuel rods.
Close. So this is, yes, in the nuclear fuel vertical, but these are actually triso fuel pebbles. The particles in triso. So this is a new type of nuclear fuel that is anticipated to be used for the next generation of nuclear reactors. And this particular thing we're looking at is called triso or tri-isostructural particles that we can go into later. But we recognize that the nuclear fuel supply chain is a bottleneck towards increased deployment and is yet a new area that we have launched into. And just want to highlight again, the folks here working on this are Bennett and also Peter, who's with us today in the crowd. So many of us know that we are kind of in a new nuclear groundswell. We're a new nuclear renaissance, dare we say. And there are a couple of things that might be different this time, as there have been prior nuclear renaissances. Number one is that we have significant load growth, this time driven by AI and electrification. The hyperscalers that are driving that also are now placing a premium on clean, firm power. And there's more and more increasingly a discussion and focus on energy security, safety, and capacity. So that's kind of the context in which we're living in. But nuclear fuel costs, even though they promise clean, firm power, is that their costs are rising at a very critical time. And then there are a couple factors here that are leading to this increased rise of prices. There's going to be, for example, a ban on Russian materials starting 2028 that places a lot of stress on today's supply chains to shore up, where suppliers and players are shoring up their supply chains to ensure that they can withstand that kind of impending storm. And that is placing a lot of upward pressure on the price of fuel. Now, simultaneously, natural gas prices are trending down. And of course, natural gas is really the competition that nuclear has to beat. So the continued success of nuclear really does rely on the fuel competitiveness. And whereas we're seeing a lot of interest in nuclear in the industry today, and investments and startup activity, and of course in the lingo of the new administration, we recognize the fuel side is an overlooked aspect. And it's important for us to continuously skate ahead of the puck and address issues before they manifest so that we can do something about it. So that's really the impetus of this work. Now what's become a trademark of STEER analysis is to really, at the beginning of when we start new activities, is to fully map out the value chain and really understand how assets, how dollars, how technology, and ultimately electrons to the grid flow. And so this is an example of what we put together, where we identify those in the mining space and how materials flow from mining to conversion. This is the step in which uranium mines are converted into a gas. That gas is then enriched to make low-enriched uranium for today's reactors. But a similar process needs to happen for next-gen reactors, which use a higher enriched form of fuel known as HALEU, and how these flow into yet the next value chain vertical focused on fuel fabrication, and that has both conventional as well as next-gen fuels. And that ultimately flows to the utilities and to, of course, you and I as customers on the grid. But there are a lot more other pieces to this puzzle. There are, of course, the people developing new reactors. There are those building the actual equipment and installing them onto in major construction sites. There are those that are now pure play doing this kind of development for the sake of cost. And we can understand the complexities of how dollars are flowing in this entire ecosystem and who has power. And of course, understanding the regulatory framework in which this exists in. And so again, coming back to the convening aspect, for us to do this work properly and to make sure that we're asking and answering the right questions, we need to convene and pull together all of these people in the value chain. And so that's exactly what we did. We identified everyone, all these companies are playing in these spaces. And then we again pulled together a roundtable in July just this year. And this was the first of its kind, where we had the CEOs of uranium mining companies all the way to the VPs of nuclear at utilities in the same room to really hash out and understand what do we need just not only for the low enriched uranium kind of supply chain for today's reactors, but also what do we need to do in advance in anticipation of next gen reactors that are coming down the pipe. And what we were able to do is to put together an entire Sankey flowchart of how uranium atoms flow from the mine all the way to conversion, to enrichment, to fuel fabrication, to actually being used in the reactors, and how that might be recycled in the back end to feed back into the supply chain. So here we're looking at the flow of uranium, again, but down to the level of assets. So each one of these rectangles is actually not just a company, but a factory or a mine or a facility. And so with this kind of Sankey flowchart, we can begin to ask questions like, what happens if we actually do in fact remove and subtract Russia from the supply chain? What happens if we further remove all, for example, FEOC or foreign entities of concern in today's politics? And what happens, and we can understand the shortfall of, for example, enriched uranium, and then identify what we then must need to go do about the supply chain to fix it. And so many hyperscalers today are asking the questions of, what does it take to add 50 gigawatts of new power to the grid? We can actually go identify what do we need to go build for that to happen. And what we're seeing in the black bars are the actual increased capacity in conversion or enrichment for this to happen, not only with today's reactors, but also for tomorrow's reactors. So again, I want to come back to this idea of these analytical horizontals that Sally mentioned, cutting across these technology verticals. And again, just now, the 3 case studies that I walked through really highlight these nodal intersections. So that the sodium ion analysis was really, of course, on the energy storage vertical, looking at the technology layer. The graphite supply chains is still in the energy storage vertical, but focused on supply chains. And of course, the nuclear fuel supply chain work just now was focused on nuclear and supply chains. But we have other very important work that's ongoing right now that we don't have time to talk about today. But we're really excited to push forward and see where they go. And one of the things I would love to hear from you guys as well is to see where other areas might we go into. What are these intersectional kind of nodal points that we should really deep dive into that can really help us focus on the right things to build. Now, if we reflect on just the past 2 years of STEER, I think some of the key ingredients that make this all work are 3 things. The technological rigor that we focus on our analysis, and this is really, of course, we're at Stanford, we have the ability to deep dive really deep into these black boxes, but we also need to tie that with the awesome convening power we have at Stanford to stitch together and pull together industry, to get their feedback, like Sally mentioned, and really make sure that we're working on the right problems. And this core focus on economics, again, is central, especially at a time where affordability is key. But these are 3 key ingredients. None of this would happen without, again, the incredible team we have at STEER. And our team, as you can see, is growing. If you're interested in joining us, please reach out to Will, myself, or Sally. We'd love to see where we can take this. So the last slide I'll leave you with is really, again, what does success look like for us? We keep coming back to the key questions of what to build, where to innovate, and how to invest. And I think what's remarkable about STEER is that we can help address the questions that industry has and really help them de-risk technology roadmaps. We can address questions that investors have and to increase their confidence in dynamically evolving technologies. We can help the government answer questions about where they can intervene. And of course, for those of us in academia, really help us inform the right research questions and problems that are worthy of pursuit. So with that, we'll stop here. Happy to take any questions and really appreciate your time today.
Thanks very much to all 3 of you. That was a truly exciting, and I think you'll agree, very, very timely presentation, just dynamic. Many of us have been struggling for years about how to conceptualize, let alone implement a strategy to get all the R&D and commercialization work going. We're a little bit over time, so we probably have time for just 1 or 2 questions in the room here, and then we can do informal follow-ups, and the lucky students who signed up for today will get an up close and personal for the next half hour. 1 or 2 questions only, preference for students. Okay, there we go. We have a taker.
I feel bad taking one of the only questions, but I'll go ahead. Hi, my name is Debney. I'm a master's student here at Stanford International Policy. Thanks so much for your presentation. I especially appreciated the slide that you showed about the nuclear supply chain because it shows that energy is truly an international issue. So I'm wondering how you include geopolitical expertise into your research, since this is such an important element of what you're researching.
Well, I think that the short answer is there's a lot more we can do in that domain. I think at this point, we, awareness, engagement. So, for example, at the graphite workshop, we had people from Australia who are very interested in these issues. But I do think it would be really helpful because at the end of the day, we're not interested just in a U.S. energy transition. This is a global energy transition. So we need to find partnerships. And also from my perspective, we don't need to have everything here in one place. we need to have cooperative relationships, but we also need a certain degree of security, because if we've built up an industry, a battery industry, and supply chains, get cut off for them, that would be, very, very damaging to those industries and energy transition in general. So we need to do more, and I think it's a great opportunity. And if there's anybody in the room, including yourself, who would be interested in bringing more of that dimension, we would love to talk with you.
And maybe I'd add that, at a time when governments may be in tension, academia plays a very important role in maybe actually playing maybe a diplomatic role. And so actually in our graphite analysis, we had collaboration with folks from Tsinghua who really helped bring in the Chinese dimension and really understand the cost there. And in the nuclear fuel supply chain, we were able to pull people from Kazakhstan, who of course dominate mining. And so that engagement is really important to upkeep.
One more short question, maybe. Any takers? Okay, right up here, up close and personal already. Go ahead, sir.
Thank you. So my question is if you've given any thought to research on decentralized facilities for these battery energy storage systems, because from the slides it seemed like it was big facilities that may be centralized. I don't know if you have anything on that.
Yeah, I mean, I think that is very much on, the issue of deployment models. And if you look at the grid and grid stability, and if you have the overarching goal of the lowest cost solution for clean power, where to allocate your assets is really important. So it's an important question for storage. Now, obviously, there'll be needs, some centralized storage, but also decentralized storage. But that's also tied in with generation, that if you look at PV as an example, clearly we need large-scale, utility-scale solar plants, but it may be very helpful within the distribution system dealing with bottlenecks and so forth. So that's a question. Just to say one more thing, John wants me to stop talking, but there, you'll hear people argue that having more distributed generation is better for energy security and reliability. And I've never seen the analysis, the quantitative analysis that tries to look at what is that appropriate allocation that achieves that objective of, resilience, reliability, affordability. So it's a question, and I don't know if Ines Azevedo is here. Anyway, she's another professor who works on some of those issues. So yeah, happy to talk more about that as well.